Francoeur, our next speaker. I like the way he describes himself as a self-learned independent inventor. He's working on alternative energy all of his life. Now he's turning it into a business. He's had many jobs, something I very much sympathize with him on. I used to tell people I was an expert in careers because I'd had so many. He's always been aware of an ether ever since he was a young boy. And so the ideas flow into his mind to help solve the energy crises that we have created. So he sees this vapor technology as an interim until dynamos and free energy machines can come out, because there's going to have to be a period of changeover, and he's very realistic about that. He's working on multiple technologies simultaneously. He lives in Penticton, which is about 5 miles east of Vancouver in British Columbia. So let's welcome Francoeur.
Thank you, everybody. Test, test. We can begin. Good morning, everybody. I'd like to talk about the vapor system and the interference disk generator. And I'd like to talk about the vapor system, the interference disk generator, the permanent magnet dynamo, and a little bit about the EMA system of Edwin Gray. This is just to show some of the materials that I use, the kind of materials I use to construct the vaporizer. It's a 2,000 PSI stainless steel pipe used in the refining industry of gasoline. And this is the vaporizer system looking inside of it. And as you can see, I don't have something working now. We got a dead battery. Pardon? A dead battery, I think. Okay. Right here is a cold start nozzle from a Volkswagen Fox. This is where the fuel goes in. And this is where the return line of the fuel goes back to the gas tank. It goes through a cooler so that the fuel goes to the gas tank always cold. And right in here is packed with stainless steel wool, including... Okay. And right in here is a 200 mesh stainless steel screen on all the way around it. So, and right here is a filtered air inlet that pulls the vapor out of the gas tank. And right here is where the heat from the engine is cycled through the system. In here, around the pipes, and goes in and around the inner cylinder, and comes out again back to the engine. So we just take the heat from the engine and circulate it through the system so that this heats up. And out here, this is another screen, fine mesh screens, packed with stainless steel wool, multi-layer, so it doubles as a flame arrestor. And this also works as a mist separator to separate little droplets of fuel that may be flying around in there. And right here is where it's delivered to the engine. Okay. This here just kind of hard to see, but some of the measurements, it's I don't know how well you can see that. 4.5-inch diameter pipe, approximately 10 inches, 12 inches high, depending on how big you make the screen on the top. And, okay, show the next one. And this here is when I was putting it together, just before some of the welding was done, and these are some of the ring components of the top and bottom of the chambers before they were finally assembled. And this is the completed unit. This is the one that was installed on the Ford station wagon with a 400 cubic inch engine. And right here are the throttle body plates that I use that were mounted underneath the venturi. And this is what created the vacuum to draw the vapor in. And right here I have two of them, pretty much finally assembled. And just thought I would show them so you can get a nice understanding of, this is the third one that is not yet completed. It's going to have many of the improvements that I've gained out of these previous two. Right here is the stainless steel nozzle, the cold start nozzle from the Volkswagen. This is the filter on the top that separates the mist in the fuel. And this is I use stainless steel lines for the fuel injector circuit, so it's for safety. Okay. And these are the variety of induction systems that are available, so you could put them on any kind of engine that you have. Big blocks, small blocks, 4 cylinders, pretty much anything. And they're used in the propane industry as a dual fuel circuit. And they are a dry vapor system so that it'll draw the vapor in the engine, using the engine vacuum. And that's how I metered it into the engine. And what I did is hooked up a valve, and that valve was linked to the carburetor butterfly valve. And I would synchronize the two together so that to control the mixture as close as the optimum as possible. This here is a diagram that shows the flow circuit. Right here is a filter that filters the air before it goes through this one-way check valve where the air is introduced into the fuel tank where it pulls all the vapor that's always in the fuel tank. And right here, the vapor then is brought up to the fuel line where where you fill the fuel in the gas tank. And it goes up here into another check valve. This here is to ensure that the fuel in the pool does not run back down. And then it goes through the screen where it bubbles in the pool of fuel that is the same height as that return nozzle here, where the overflow fuel is then pumped, goes through a cooler so that it is returned to the fuel tank cold, not heated. The heat from the engine is either exhaust manifold heat or hot water. My previous experiments were using the engine coolant. And I basically plumbed it in here, goes there through the vaporizer, exchanges the heat, circulates through, comes back down. It goes through this line here, which is something that evolved out of the circuit based on my experiments, a trial and error. I had found that when I was running this system, once the fuel vapor is heated, it has to be maintained at a temperature to prevent it going back to a liquid by the time it was delivered to the engine. So, and being in Canada in the cold winters, I needed to have something to prevent that. So I built this line out of stainless steel and welded so that we could heat the outside of the line, and that would maintain the temperature of the vapor all the way to this valve, which is the venturi that creates the vacuum, and where it's metered into the engine. And it's a system that basically becomes a dual fuel circuit. I made it so that I could switch it on and off. Something like if you had a propane-powered vehicle that had a dual fuel circuit, you can also turn that on and off. I basically did the same thing, so I left the engine as original as possible, and if it worked on carbureted engine or fuel-injected engines, depending on, I had both, so I tried it on both, and both times it was a dual fuel circuit. So in case I had problems, which I had bugs to work out, I could pull over and switch it off and carry on. And here, basically, I took the color out just so you can get an idea what the gasoline here and the vapor is drawn through, and I describe it's kind of blurry. But you can see the air filter and the air inlet. The air goes into the carburetor here. So there's two sources of inlet, and well, you don't see the bottom. This leads out back to the exhaust system. And that's the circuit that I used for the vaporizer. And it worked. But it's evolving better. I have another generation that I don't have available here right now, but I'm working on in order to eliminate this return fuel line, and and there's another line here. This here, I forgot to mention, is a dual tank switch. If you have a vehicle that has dual gas tanks, you have a switch that allows you to run one or the other. I did that, and that allowed me to shut the carburetor or the fuel, shut the delivery of the fuel to the carburetor or the fuel injection system, and deliver it to the vaporizer, and that's one way I used to turn one on and turn the other one off and simultaneously back and forth. Okay. Okay, this one here is the car that I used, a 1973 Ford station wagon, and this is during the assembly and the installation of the system on the car. And there's the vaporizer here, and I used 2 fuel pumps for the return line for the initial experiments because I wanted to make sure the fuel got back to the gas tank so that it didn't overflood and flood out the engine. I had a few of those during the experimenting. And this is the device that goes in between the carburetor and the intake manifold. It worked, but the next time around, I'm going to relocate that to above the butterfly valve so it gets a better mixture ratio. And next one. And again, I just show a different angle of it. And this is the line in the early ones. This is before I put the self-heated line in. I used the same off-the-shelf components that are used on propane and alternate-powered vehicles. So there's no sense reinventing the wheel when I can use what they have available. And I use it to plug it into the vaporizer so it supported the functions of the vaporizer. And everything else I need, I pretty much manufactured in order to, like, for example, the vaporizer. And I manufactured my first Venturi, which is underneath there now in this picture, whereas the one on the next picture, oh, that's the one after that. This is just a side view. So, boy, they're not very clear. But again, you can see that there's 2 fuel pumps there. The primary fuel pump is further down the line, and that pumps the fuel either to the carburetor or the vaporizer through the switch, so I can, as a dual fuel circuit. And then that switch was also connected to the return fuel line, so that when I activated the switch that diverted the fuel, it also activated the return pump simultaneously so that it continually pumped it out as the fuel was being sprayed into the system. Okay. And again, another view. This one here shows on this device, on this car, I used the engine coolant heat right here. And basically, it's the same heater line that goes to your heater in the car, and I just put some wide lines in there and diverted it to the vaporizer and circulated it and back to the engine. Okay. This is the next one I installed. Is on a 1989 GMC 454 one-ton crew cab truck. And I have the dinosaur vehicles. They're obviously inefficient on fuel, and I figured it would have the most dramatic effect by putting them on these vehicles. And here it's kind of hard to see, but the vaporizer is right here. And I insulated this line. This is the self-heated line so that we can deliver the vapor to the engine while maintaining the temperature of the vapor so it doesn't cool, and that worked. And right in here is where I installed a dry vapor valve that was controlled by a box here that's connected to the O2 sensor, and that was my early attempts to have electronic feedback to control the mixtures of the vaporizer so I could eliminate the linkage that I used before. And it's a pretty simple circuit, and it's evolving again as I do more tests and I find problems that I have with the system, and then I work them out and do more machining on the stainless steel and try it again. And so it's been a trial and error and refinement each time I go. And my next generation vaporizer is going to be a little more elaborate than this one. It's going to have a 2-part system, one for the preheating using the hot water coolant, and the other one would be for 450+ degree temperatures to deal with the heavier fuels that tend to circulate when using lower temperatures. So when I up the temperature, then we're going to see how well that works to crack those heavier fuels to increase the efficiency even more. Okay. This is another angle of it here. Hopefully it's a little closer. Again, there's the line here and right here. And I have a shutoff valve here, a manual shutoff valve. It was too expensive to get all these fancy electronic solenoid-activated valves. I worked with a low budget, so I didn't mind opening the hood and shutting it off when I had to divert one to the other. But in the future, when it's integrated with a computer feedback system, all that will be part of it, all those automatic valves, so that when they switch it on and off, I can get away from using manual valves. And this is the little computer board, and that's basically what I did there is just adopted technology that is already available for natural gas and propane-powered vehicles. But the problem I had with that, it needs to be recalibrated to deal with vaporizer from gasoline. So there you have it. There's the vaporizer, and that's basically how I did it. And the results, because of ongoing flooding, or not flooding, I should say, vapor lock, because of the way the return fuel line is set up, I tend to every now and then gulp the vapor would get sucked into the return fuel pump and cause it to stop pumping for a while, which would then fill up the vaporizer, and then I would get an overflow and flooding. Then I had to shut down and then flush it all out and start again. So it shows indications of increased efficiency, but I have yet to get real actual mileage, how much mileage improvements I'm getting yet, because I really don't know that. But the goal is to really get as much as I possibly can without leaning the engine. If you lean the engine out, well, that's not good. So, next one. Again, this is another angle. You can see the truck. I used to snowplow with that truck all over BC as a contract. So I was using that to cut my fuel. And this truck is a three-way system. It's gasoline, regular fuel injected, and it's a propane system, as well as a vapor system. So it's a three-way, a little more elaborate than the car. And I wanted to compare the test results between the vaporizer fuel system and what's on the propane system that's on there now. So I had two Venturis. This one here was for the propane system, and the other one was installed underneath the throttle body and the intake manifold, so that it was also a separate circuit from the propane system. So I had a switch where I can switch one or the other or the other. And, okay. These here were on the Ford when I did an emission test, and it shows to be a lot cleaner than the carburetor. And we like to keep the ratio as, 13, 14, 15, but not much higher, but here it shows a little bit. The hydrocarbons is there you go. Okay, that's what I need. Just to compare. The idea was to remove as much of the unburnt liquid vapor from the jet stream as possible without starving the engine or running it lean. And if I keep the ratios as close as possible, the engine will produce still the full power that it's designed to do, other than the fact that I'm cycling out the waste that would otherwise be burnt in a catalytic converter. It's waste. So what we're doing, the vaporizer cycles it out and pumps it back into the gas tank, and we deliver vapor fuel to the engine and treat it as if it's a propane or natural gas. And there you have it. And this here are the comparisons. We have a higher oxygen content than normal, because when the explosion takes place and the work is being transferred to the piston, that's all we need. After that, the flame is out because we've extinguished the fuel already. We've burnt it. And we don't have a continual burn at that point, consuming the oxygen, because we've already removed the unevaporated fuels from the system beforehand. And that's why we get an oxygen increase as compared to a regular engine, which uses up the oxygen and makes all the pollution. And therefore, in the early 70s, they put an air pump on the cars to replenish the oxygen supply and burn the unburnt fuels in the catalytic converter in an attempt to clean up the emissions. This cleans up the emissions. That's compatible with propane gas, while at the same time extending the range, because we recycled the waste fuel so that it can be used by converting it to vapor. Okay, I think that's that one. During all my life, I've always been interested in this field of energy and ways to make devices more efficient. And I've always had a little bit of a viewpoint. And I started constructing this machine actually in Yellowknife, Northwest Territories, as a result of me working in the mining industry and working next to 1,000 horsepower motors and generators that they had on the plant. And I operated the equipment, and I was always exposed to it every day, and it made me think a lot of electromagnetism. So I figured there must be a better way to create electricity. So I actually heard about Eklund and studied his work a little bit and elaborated on that further. So what I've done here, we can flip the page. This is the very first one, using Alnico magnets. And this is the second version, which I replaced it with stronger ceramic magnets. All the coils in here are horseshoe coils, and they're all amorphous material. What this shows is that I mounted the coils and the magnets stationary. Open the air gap a little bit, inserted a disc that's magnetically balanced for easy turning. Rotate that disc, load the coils, the disc does not slow down. Kept on going without a change in its pitch. Very interesting effect. And one disc differs from the other in the fact that one has 10 fins and the other one has 11. That allowed me to change the phase of when the coils have their peak cycle, depending on which disc. For example, the 10 disc here, you can see that coil, and those two magnets will allow the coil to pulse in phase. So I can take those two coils and put them in parallel or series to build the volts or amps to any desire that I wish. And it allows you to also get a three-phase system out of it. Just simply by altering the distance between these discs, it changes the phase. And both of them showed that under load, neither of those discs slowed down while the machine was loaded. Okay. And that led me to building a bigger machine and doing something more to it. I used cores that were that shape, and I made them out of iron nickel met glass alloy, amorphous material. And these are 5 inches long, 3 inches wide, and they're a 1 inch by 1 inch core. Okay. I could not find a rare earth horseshoe magnet anywhere. Nobody could make one. I've inquired with many, many magnet plants, including the ones in China, and they couldn't do it. They cannot bend the neodymium material. It destroys the magnet in the process. So basically what I did is machined one. And this is the key here. But I machined it in a way for that shape in the direction of the magnetic field. So that when I placed it inserted on the edge here, these here are bar magnets right here. You see here, 3 inches long, this one. And this here allowed the magnetic field to be bent around the corner, forming my horseshoe magnet using neodymium grade 35. Okay. And this is what it looks like, the effect. I thought I'd show the drawings along with the actual machine here, and what happens when the disc turns. You can see up here, the opening slots here allow the induction to take place into the coil. As the flux surges the coil, it creates our induction. And then as the disc turns, it switches sides. This side closes off, and the other side opens up, creating an induction the opposite polarity, giving us AC power. Okay. This is a side view of how there are 6 coils. I designed each coil for 300 watts output, but I have yet to get it yet because I have some problems with the disc. My budget ran low at the time, so after spending the big bucks on building the machine, I only had a couple of hundred left to use a soft iron plate to construct my disc out of, just to get the machine going. But that created problems in the fact that the magnets were so strong, it would actually warp the disc that would destroy the magnet if I didn't shut it off and open up the air gaps. And then, because of that, I have to redesign the disc. that are much more rigid to prevent them from collapsing into the magnet. And then from there, I can close the gaps and increase the energy coming out of the coils as a result. Okay. And this just shows a side view, and I thought it was a good way so that everybody can get an easy understanding of how I put it together. These are the E-bars that I use to hold the 3 main plates together. And there's connecting rods that go through here and here. That allows me to adjust the gaps on the machine. Okay. Another 3-dimensional view. Oh, it's kind of dark. It's kind of. And here I don't have anything. I just assembled it. I was beginning to assemble here. I thought I'd photograph that so you can see what the plates look like. And the coils are here again, the E-bars, and the magnets are housed here on both sides. And there you have that. And I'm reviving this machine. I'm redesigning the disc, and they're going to work actually quite a bit different. That will prevent them from collapsing into the magnet. But that's going to be a rework of the way I build these E-bars. I'm going to remove them from this part of the machine so that I have a disc design that will allow the tops of the disc to connect to each other, preventing them from collapsing into the magnet either way. And that will allow me to have minimal air gaps for maximum flux transfer to the coils. I used a 1 horsepower motor to test it, and that's all it was a test motor. It's a 1450 watt motor that consumes a lot of energy. It's very wasteful. But the interesting thing that strikes me, and I'm still fascinated by it, is the fact that it just does not slow down when I load that coil as compared to the next upcoming generator. I think it's coming up now. Oh, okay, I thought I would show another picture of each one so you get another view. And I was not able to light up this light bank yet on the load because of the disc problem. But when I revamp the disc, then I'm going to reconnect it again, and hopefully we'll get our full 1,200 watts or so, or 1,800 watts out of it that we're looking for. Okay. This here is the earlier version that we could amplify it by multi-layering coils and magnets and disc and coils and magnets and disc, and offset the disc so that each disc has a static hold that's right here, for example. It's dead on to the magnet. That's where we have our little bit of a bump. And this here, multi-layering it, allows us so that we can stagger each disc depending on which layer we're at, so that we can reduce that lock-on position right here by balancing it off of each other, balance one against the other. So we balance the disc in relation to the magnet, and then we can balance the disc in relation to the other disc, depending on how we position each one, set them out of phase. Okay. And this brings on the interchangeable permanent magnet dynamo. Right here I show the system with 12 magnets and 12 poles, which allows all the rotors to be pulsing in phase. Therefore, I can put them all in series or parallel, basically dependent on where I want to build my volts or amps. Okay. This is what the coil looks like. It's all micarta or phenolic materials, and it's machined to these specifications with a quarter-inch threaded rod in the center. And right here is a backing plate that's installed right up in here. And that's for the winding of the coils. This is what it actually looks like here when it's finished, before it's wound. Okay? And next, please. Here I show a couple of them being produced basically on our kitchen table. And this is the material that I use to wind the coil. This is the cobalt amorphous metal. from Honeywell. And very expensive, but it fit the application. And I tailored the design of the core, each coil based on this material. Okay. Right on the kitchen table. My wife's been a big help. It takes 4 hands to build these coils, and each coil represents at least 12, 16 hours worth of work. It's a several stage process. I assembled, once I build the phenolic cores, I wind 59 feet of mech-glass material on each core, which makes it be a 1-inch diameter core, 2 inches long. And from there, we mount it on the vice press, and then we wind the coils accordingly, 1 layer at a time. And the output of the coils are basically 100 watts each, give or take, depending on your load and the speed of the machine. And next one, please. This is they're a little dark. Okay, this is a variety of angles showing. We have several of them. We tested high voltage coils and low voltage coils, just to basically find out it's 600 RPM and the machine's producing 60 cycles. So I built several coils that uses 735 layers, turns of number 18 wire, and 2 of them in series gives us 115 volts at 600 RPM with 60 cycles. Okay. This is one of the mounts used to support the coils. As you can see here, this back piece here is inserted, and there's a nut that holds it in place that allows me to interchange the coil in and out, put a different coil in without changing the rotor, without changing the machine. So if I want a coil for a DC with a different volts or amps, I could take that out, put it on the shelf, and put another one in that's designed to give us that. So it becomes completely interchangeable. I could also remove the entire rack itself and put in another rack that's already preset for it. This is another coil mounting rack, but it's a little bit different in the fact that I use this to function as an impulse system. The previous coils were dynamo coils. These are for the motor part of the circuit. So I experimented also with impulses. The core is it's a 3-inch long core with a 1-inch by 1-inch nickel iron alloy mixture, and that's exactly what it looks like. And there's 3 along the top and 3 along the bottom, and I hooked them up in 3-phase. Okay, please. And this is another version of that coil mounting brackets, but it has 2 different kinds of coils. The one in the center here is designed to function as the dynamo coils, and where I installed 2 of the motor impulse coils on the outside. And this is going into the area of an attempt to convert the machine into a cross between what Tesla's dynamo and Ed Gray's circuits. Next, please. This is a cutaway view of the rotors. All these rotors are precision machined based on phenolic materials, and I constructed a steel keeper ring that's precision machined so that the magnets are attached flat to the surface. And that allows the keeper ring to function as the neutral zone, becomes the middle of the magnet, so that the magnetic field that was once in the center is now pushed to the outside, increasing the magnetic field density toward the coils. It made for a very powerful rotor as compared to if I use a disc rotor, and it keeps the machine as small as possible. Okay. And this is what 3 of the rotors look like when they're completed, minus the stainless steel side plates. And you can see here, it's hard to see, I suppose, but they're angled. Each coil is offset by 10 mechanical degrees, which allows the coils to operate in 3-phase. So they're 120 electrical degrees apart. Okay. This is the side view showing the impulse coils here, and here. And this here shows a cutaway view so you can get an idea of basically how it's put together. And this is when I hooked up the three-phase brushless motor controller that you can buy on the market now on permanent magnet brushless motors. I basically did not use their motor, but I just purchased one of the electronic control boxes and adapted it with this using Hall sensors to control the timing. And it worked well, but it only didn't give me any more efficiency than what the controller could provide. It was not producing radiant energy. So that led me to, well, I got to change the way I run it. Okay. This is when the machine is assembled, minus the winding of the coil. And you can see here, the top and bottom opposite coils are always in phase. Those two are either, I can hook a parallel or series, and they're also in phase with one here. Those two that are opposite of this one on the second inner rotor. The third rotor is also in phase right here, right here. So all 6 of those coils can be connected to be one larger dynamo. I can put them in series or parallel to build the volts or amps depending on what the application requires. And if I needed to change it, then I could have a separate circuit. This machine will hold up to 5 independent single-phase generators. You can see here, all the coils are isolated from each other, and we got 1, 2, 3, 4, 5 phases. So each bank has 5 phases, and each phase represents 6 coils at approximately 600 watts each. Okay. This is the single rotor application. The motor is interchangeable to 1, 2, 3, 4, 50 rotors, however many rotors you want to put on the shaft. You just offset them each in relation to the other and spiral them so that you reduce the static holding force and reduce the torque needed to crank the rotor for startup. And this test, using this 1 horsepower motor, I use that motor just to test the output of the coils, but I don't use it as my final solution to making it run on its own or anything like that. So this configuration only showed at approximately 45% efficiency based on test results where I had a fellow come over and use his meters, and I have to take that as more accurate than the ones I have. And so it was clearly not impressive on my part, so I realized that I'm going to change the way the prime mover works. Okay. Again, here I show the motor running under test. Took pictures of it. Just at different angles, using the 1 rotor version. 6 coils would light up, well, I can get 1,200 watts out of it, or 12 100-watt light bulbs fully illuminated. But then the motor would get very, very hot because this machine doesn't behave like the interference disc generator. It wants to slow down when I load the coils. Some of the differences between the two. So I tried the other test. This is the one where I hooked up the AutoMotion brushless motor controller, and I got it to run, and as soon as I started regenerating the energy back, pop, one MOSFET after the other, they blew like popcorn. So each and every time I would dismantle the controller, I'd put a new set of MOSFETs in there and get her going again, and every time I attempt to close it again, they would fry them again like popcorn. So I gave up on conventional brushless motor controllers at that point. Okay. This basically, I have, the EV gray motors right here, the interference disc generators right here, and our dynamos here. And many of the coils right here, I designed them to produce 12 volts DC after they're rectified, to energize these capacitor banks here. So it's leading to a new set of tests so I can energize these capacitor banks in parallel and add them up in series and get a higher voltage impulse. And I haven't completed the results of that, so I won't have that information until a later date to see how well it will change the efficiency. Okay. Again, one interesting test I did, I don't know if I can I don't know what to call it, or I really don't know how efficient it was, but I'll just describe it like this. If I draw 15 amps from the battery at 12 volts and pump it through this motor, it's rated at 13 amps. I load the coils, and it gives me back a little less than 15 amps at 12 volts, and I take that energy out of the regenerating coils and actually circulate it back into the motor. And the motor would now increase its load to 30 amps, while I'm still only putting in 15 into the system. So I was circulating the 15 around and around from the regenerating coils, which was overloading the motor, creating excessive heat out of the motor without creating the same heat out of the regenerating coils. The motor ran a lot hotter, the coils would just be more like warm. And that was my attempt using battery power to see how long it would run on its own. And it would only run as long as the battery would hold its charge. But the interesting thing that struck me was the fact that I'm still circulating that 30 amp through the motor, getting hot with only a 15 amp input. And from there, I don't know the efficiency of that, or what you would call it, if it's over unity or not. So that's why I reserve my opinion on that until a later date when we have proper test equipment to confirm or deny what's really going on. Okay. And this here again just shows that if I put a 12 coils around the rotors, then they'll all act like one single generator as a single phase machine. And if I layer each rotor with 12 coils and offset them, now we increase the potential of the machine. It becomes, well, 1,200 plus watts per rotor, and and that'll increase depending on how many rotors I add to the system. And okay. And that led me, and then while I'm developing all these technologies and paralleling them at the same time, I basically would develop each one a little bit here, a little bit there. I didn't want to leave anything behind, and that led me to an opportunity to acquire the Ed Gray's motors, number 4 and 5. And I've learned a lot since then, and I'm still learning more. And when I got them, they were actually quite rough shape, needed cleaning up. There was some damage to them, so I dismantled them. And this is motor number 4. And I opened up the coils. They could not run in the way that I received them. The phenolic pieces that were inside, I think it's phenolic. It's a green, I think it's a fiberglass grade phenolic. And it was all broken up, so I dismantled the coils to find out what they were. And it's a number 14 wire, and about 160, I can't remember the exact numbers, I do have them written down, but it's about 160 turns of wire on each coil. They're not, I've had people tell me that they were iron wires, but that obviously was not the case. And he used a silicone. It appears to be a kind of silicone, like a gasket silicone you would use on a gasket on a valve cover, as the insulator inside the coil. And it was a heck of a job getting it out and made a heck of a mess. And these are the damaged pieces here, and I rebuilt those same pieces. I didn't build new ones, I just reconditioned the ones that he had, re-drilled the holes and refastened them together and cleaned them all up. And basically, the next stage, as I ripped apart the cores, or dismantled them. And here, I posted on the internet. If you punch it by name on the internet, this will come up. You'll find that I do have an article that will detail this in more detail. It appears to be laminations that are just conventional. I'm not sure the kind of metal he used, but he did not use amorphous material at all, which is going to save me money in the long run because I don't have to spend a lot of money on Met glass anymore. Gray used conventional laminates, so we can do the same thing, which will cut the cost of these machines down. And what I did is dismantled each layer, cleaned them up, and reassembled them after I removed all the corrosion and all the grime that was on there. and set them up with conforming compound to insulate each layer from each other, and reassemble and cure them in an oven for 2 hours to cure the material. Okay. And this is nylon, and that's to insulate the coil from the core. And the end caps are fitted on the end, the ones I repaired that are made out of phenolic, right here. And that's what it looks like. And they have an unusual shape to it. This one's on the rotor, and this is on the stator. Okay. And while I had them apart, I drew the pattern of the core. And there you have it there. And I placed them as close to the 12 o'clock position as I could guesstimate it. And they seem to be offset. Well, he did a very good job building the motor. And from there, this is after I reconditioned motor number 5, and I left Ed Gray's writing intact. I figured that was necessary. And this is after it's completely dismantled and after I reinstalled it, all cleaned up and ready. This motor is now basically ready to run. This is number 5. Okay. Number 4 and 5 are virtually identical motors, other than the fact that they're made out of different materials. The coils and rotors are interchangeable, and all this brush assembly here, it'll plug from one machine to the other. So that's one thing I found very interesting, because I can reconstruct the same coil and upgrade motor number 4 to have the same horsepower capability as motor number 6 without really drilling one hole in the machine. All the holes and provisions are already installed there for it. I think Ed Gray was planning to do that, but for some reason he didn't and went ahead and built number 5. Okay. Number 4 is not ready to run yet because there's a sleeve here that has to be replaced, and this is a nylon sleeve that covers this motor in order to insulate the coil from the shaft itself. That broke apart it was brittle, and so that's one piece I have to replace. And this is the first motor I want to run. It has one coil on the stator, one on the rotor, and that allows one pulse every RPM. And that'll be the first one we run in order to fine-tune the circuits to reproduce Ed Gray's rated energy circuit. And this is the final reassembly of the EMA motor number 5. And the commutator is here, and this here is integrated into the pulse switching circuit with the switching tube. And this here is an aluminum ring, and there's a letter, it's like a letter, a horseshoe shape in a sense. And this has this is 2 contacts. And one is to maintain the contact between these points, and the other one is to maintain a continuous contact on an inner ring. So that allowed, based on the position of the coils, to control the pulse. Okay? Okay, and this is a close-up of the reassembly of the motors. I removed all the bearings on both motors and took the best of the bearings, they're identical, and put them in this one, but I have to replace the bearings on motor number 4 because they're damaged. The seals are gone and the bearings weren't usable. And one thing I noticed, I first thought this was motor number 7, but I had found out, I had learned that it was motor number 3. But one of the things I'd like to point out is that, this motor doesn't look to me to be an aluminum motor. It looks to me to be a nylon motor. And why I think that is right in here. These parts here, the way that's put together is identical to motor number 4. And being this motor number 6, sorry, I've made that identical to motor number 5 because they're both nylon motors or phenolic engines. But motor number 4 seems to be similar to the motor number 6. So he seemed to jump from one material to the other. I think this one here was there to contain the electroradiant effect from broadcasting in the medium. So maybe he used the metal casings to prevent that. And this is a proposal that I would like to try out, that when I get the gray motors running just like he had them. My plan is to run them the same way he did it first, to confirm it and do a whole new round of testing and find out how much power they produce. And integrate it with the dynamo to see how much electrical watts the motor as a prime mover can produce in the dynamo. I'm not there yet, but that's what I would like to try out when I get everything finalized. This here is just Mobius coils. I constructed them. They're all mech glass material. It took me 2 weeks to wind one core, and I had a big pile of the ribbon piled up on the floor, and it's as sharp as razor blades. So it's basically a piece of paper. You twist one half, and I had to ring it through, and every layer, and ring it, just like knitting. And I haven't really tested them yet, but my plan is to see what happens when I impulse very short unidirectional DC energy to see what happens, basically, if they get too hot or if they lose weight, or I don't know. I want to learn. So that's why I constructed those coils in preparations for that. And there we have it. And this here just shows them this is after I cured the coil, and I began construction of one that's much larger. And at first I thought, well, maybe I'll try and make it a meg out of it to see if it would do anything, but I haven't gone that far with it, and I actually changed my mind on that. I'd like to impulse reading energy out of the circuits once I get the switching circuit tube working again. And with that, oh, no, I don't think, boy, oh boy, where are we here? Okay, basically from there, that's where I am today. I've got this far, the dynamo's constructed, and I've got a couple of large, I think we showed them. This is where I got the picture from, and I blew it up, and I wanted to study the conversion tubes a little bit. So the shaft on the motors that I have are 30 inches long. And here I'm using, this motor is larger, and I guesstimated it's approximately 6 inches, or sorry, 3-4 inches longer of the core, because there it is, okay. Okay. The motors that I have 3 bolts that hold on to the coils. This one has 4, so it's a little bit longer. And so taking that into account, this almost looks to be, to me, I could be wrong, but approximately 8 inches across, 4 inches across, which gives me an estimate of the size of this tube. And this picture would be difficult to see, but if you look on the internet and look at this site and blow it up to maximum, you'll see that there is a dividing wall, okay? A dividing wall between here, you can actually see a little bit there, okay, and here. So that kind of tells me 3 different tubes, and if we look at if this looks to be 4 inches here, from the outside collector tube, they look to be approximately 3 inches across at 4 inches long, and so based on that observation, I'm going to probably build the tubes on that dimensions and give them a try. And I'll build several. One a little larger, one a little smaller, and test them all to see which one gives the best results. And from there, I can move forward to refine the tube and recreate the tube. And the capacitor banks that I have are 5,000 volt DC. They appear to be similar to these ones. I had them designed for a very fast rise and very fast discharge. And I'm going to actually experiment with the triode and the thyrotron to determine which one will work better for this circuit. They both have an advantage and a disadvantage depending on the application. And I don't know which one will be the final tube, but it'll be one or the other after I carry out the test. And I hope to, when I get the motor running, just like Gray did, I'd like to be able to have everybody see it. I have another fellow that is building a table for me to replace, so I can mount the motors just like what you see in the picture here. And when it's ready, it's going to be available for everybody to come and see it with your own eyes. And I insist on everybody to bring their meters and let your meters be the guide, because they'll probably be better than the ones that I have. And from there, there's your update of where I am. Thank you.
Okay, we have about 7 minutes if anyone would like to entertain questions with Alan. We'll do it from that microphone over there.
Well, no, we need it on the tape, though. Go ahead and tell me, I'll tell the question.
All right. He needs more money.
Absolutely. I'm not going to pretend. I've been pretty much paying the cost the entire way. I've taken on a lot of different jobs in my life, and after paying the cost to live it, and I get the crumbs left out of the budget. And it's taken me a long time to get this far because I've worked and I put a little bit each time I had extra money. I've had some help from some people in the past who have donated some monies and some parts, but it's never been enough for me to complete the job. So I hope to do it sooner than later. And I haven't won the lottery yet, so maybe one day if I do, then that'll change everything. But right now, I just want to get the motors complete and running basically as fast as I possibly can because we need it in the world now, not yesterday or not tomorrow. We need it now, today. Okay.
Hi, Al.
Hi, how are you?
I'm sorry I missed the first portion of that. How were you able to obtain EV Gray's?
I had heard it on the internet. I'm always researching the field, okay? And I had read an email, it came up, and I knew what they were. I was already studying the EV Gray system, and I had heard about them first in 1985, 86, but I never dreamed of the day that I'd ever own them. And then, well, when the opportunity came, I jumped and scrambled and clawed and scratched and bought them.
Excellent. Were you able to? Were these in the possession of EV Gray Jr.?
No, they weren't. The person I bought them from asked me not to reveal his name,
Oh, okay.
Okay. I have to respect that. But I'm very glad that they recovered them, that they weren't lost, because it could have been lost and we would have always only had the patent to work with. At least in this case, we have the motors. And one of the things I'm going to do is I just have installed, we've got a whole whack full of three-dimensional AutoCAD blueprints, and I'm going to re-engineer the motors so that we can reproduce them. Anybody will be able to reproduce them. So I'm going to make the information available.
That's amazing. Okay. Thank you. Appreciate that.
Really quick, you might, for the sake of the video, and people who are not familiar with the EV Gray motor, just remind people what the EV Gray motor is capable of doing.
Okay. The motors that I have are, I've heard of two reports, one of them being 90 horsepower, the other one being 100 horsepower capability. I can only go by what's already available out there. So what I want to do is basically get them running again and bring them under a modern set of testing to confirm or deny what is on the internet, to demystify it. And it's a series of high voltage unidirectional DC impulses, and that creates the electroradiant effect, which is the motor turns it into horsepower, and that's basically the science of it. If you want more information there, please get it on the internet, or I'd like to recommend some books that if you want to elaborate on it. The Secrets of Cold War Technology is one of them, by Jerry Vassilatos. The other one is Lost Science by Jerry Vassilatos. And the other one is Free Energy Secrets of Cold Electricity by Peter Lindemann. Though, if you get those books and read them through, you'll get a much better, clearer understanding of Ed Gray's technology. And it's linked to Nikola Tesla's magnifying transmitter. And that's what I'd like to suggest to you.
Yeah, I was just wondering if you would repeat your internet site so we can go to it.
Okay. If you punch in a simple letter, ALF, energy, all of it will come up. Okay. My email address is al.f@telus.net. Okay. So all you got to do, it'll come. Use a Google search engine, and you'll get page after page of. It'll link you to this, all this, and more.
Okay, well, thank you very much.
Thank you very
and,
much.